Partial Differential Equations by Richard Heberman. Well worth $6. Or 10 with shipping, whatever. You see what happens here? I mean, if you just rewrite this, you can. It's basically the variable, right? This is sort of u. Oh, bad choice of letters. W. And if you look at w equals to t minus x over c, what is that? That's multiplied by c. Cw is equal to ct minus x, right? I mean, it's this solution up here multiplied by minus c or something, or divided, depending on how you want to look at it. It really is the D'Alembert solution. And what this is physically is if you have a string, and it's very taut, and it's initially at rest, and you just take one end of it, and you go like that, this is the solution traveling to the right, like that. It's physically very natural what we're finding here. Whatever sort of the initial shape is you put at 0, it just propagates. But look at how easy that was to, I mean, it's pretty easy to get that with Lagrange, with Laplace transforms, right? So Laplace transforms play a major role in some of the easier solutions to partial differential equations. But I don't know, that was not taught to me in my partial differential equations class. I'm not sure why, but there's also Fourier transforms, and there's a whole wild world of mathematics, things called Green's functions, which give you much deeper and interesting understandings of these things. But I'll shut up. Here's your test. Let me. So I won't test you guys on this. I just wanted to alert you to this world. There is much beyond this course to learn, of course. So let's look at the solution to the test. I think we still got time. We got 10 minutes. Should suffice. I'm just glad that the screen went up today. I was worried. I was really worried because I don't know if I could do this in 3 feet of board space, So I think everybody can do better, but I don't think anybody really did super bad on this one. Like, so I basically what I'm trying to say is I think I found a hole in everyone's armor, but usually a different hole. Like you all have diverse talents for making mistakes. I mean, so there's a variety of mistakes, and I must say I was shocked. Like I thought for sure that okay, I got 2 of you guys on this thing here. That's not a big deal. You can fix that in like 3 seconds, right? Now that you know about that. That's pretty easy to remedy. You just didn't pay attention to that term as you ought to have. You know who you are. That's not too big a deal, really. And I thought for sure I was going to catch a bunch of you guys with your pants down on this one, but no. You guys all got that one. I was like, what? I think I've never spent less time talking about linear independence in this semester, and I've never had students universally understand. Apparently, maybe if I don't say anything at all about linear independence, I could ask really difficult questions about it. I don't know. I'm not sure what I can extrapolate from this. It's very disturbing to me.
They were the punch on that one.
Oh, okay. So it's because I hammered you guys over the head with it on the homework. Okay. I guess, yeah, that's good. See, I forget sometimes, like, what homework did I assign and a lot of stuff. I mean, this here, I think a lot of you came pretty close. So basically, the point is that for odd, you get j, and for even, you get I. And so when you look at the matrix exponential, you can split it into the odd piece and the even piece. And then this is, every one of those is I, every one of those is j, so you can just factor I out and j out. In other words, trade an infinite series of matrices for an infinite scalar series times the matrix in both cases. And that's Cauchy-Cinch. You guys should know that's Cauchy-Cinch. So disturbing it is to me that you guys don't know that that's Cauchy-Cinch. But, some of you. Okay, the majority of you don't know it's Cauchy-Cinch, apparently. But now you know. So fine. By the way, you might notice that the first column here is in fact the solution to the next problem. That's not an accident. That's because the matrix is J for the next problem. So if you had been very understanding of the theory, you could have saved yourself a bunch of calculation in here and said, I found the solution matrix in the last problem. I just have to fit the initial conditions to cosh sinh plus C2 times sinh cosh. No one did that. I didn't do it either. I decided to Laplace transform this thing just to show you guys how it works because it's fun. And it builds the initial conditions in, right? So it's pretty awesome. So the Laplace transform, big X and big Y, big X and big Y. I can solve for X because it's, well, actually I really don't have to do anything. It's already solved for X for me. Yay. And then just substitute it into the other one. And then solve for big Y, I get that, which gives me sinh. And then on the other hand, multiply by S to get the transform solution for S. And then the inverse transform, you get cosh, and there it is. Of course, you can also write this as 1/2 e to the t plus e to the minus t, and so forth. You know, that's cool. You guys made a variety of errors here. I mean, I think just generically speaking, you're pretty unstable on how to calculate systems. This one here, I saw that you guys were not, I think most people lost points here. Maybe 2 of you didn't. So basically the point here is we have an eigenvalue of 3 2 times. All right, which if I know my linear algebra, I can read from this originally. This is an upper triangular matrix, so what's in the diagonal are my eigenvalues. But here's the calculation anyway. Eigenvalue 3 2 times. So I get one eigenvector here, because this gives me the equation, basically the second component of the vector has to be 0. The first component's free, so just make it 1. 1, 0 is my eigenvector. And then I look for a generalized eigenvector of order 2. So I solve my chain equation. And that gives me this generalized eigenvector order 2, like that. And then as a general template, I'm just taking the eigenvector and the generalized eigenvector multiplying by the matrix exponential. You don't have to do this. I'm just trying to explain to you how I think of it, okay? I'm totally cool with you just writing this down as the answer. Like, you don't have to derive this. I'm just trying to explain to you where it came from, all right? Other books just present this as sort of a black box you use. Fine. But there it is. So this is the solution. I would have taken this or that as the solution. Or if you find x equals to this and y equals to that and box them, I would have taken that as a solution. I mean, I'm pretty open-minded if you've actually found the solution. So again, this is really from the magic formula with lambda equal to 3. So the eigenvector truncates everything past here, just leaves you either the 3t times the vector. When you hit it with the generalized eigenvector of order 2 in the magic formula, that drops out, but these two things remain. That picks up the u2, and that picks up a minus 3i times u2, which is u1. And that's why we write this here, because we have this formula. When we hit it with u2, it truncates down to just these terms. This, you got to be careful. Like, if you got the wrong eigenvalues, everything else you do past that point is just garbage. I'm sorry, but that's just the way it is. So you have to be really careful with these calculations of what's the eigenvalue. Like, I think at least half of you got the eigenvalues wrong here. And so everything you do after that is, you're going to get 0 as the only solution if you try to do that. Basically, is what you're going to be led to. And anyway, so if I have one of these on the final, be careful about this calculation. In this case, we get minus 2 plus or minus I. Now, you only need one of those. One of those has, like, I guess I don't need to have 100% volume, huh? One of those has all the data you need. So A minus the eigenvalue times I gives me this matrix. And so you can pick either equation. I like the second one, which is this. It gives me u equal to that. I put v equal to 1. I get u equal to that. That gives me this complex eigenvector. That's the real part. That's the imaginary part. And you use those to construct the solution. That's the real part of this. This is the imaginary part of this. And you only need 2 solutions. That's it. You don't have to do anything with the conjugate eigenvalue. If you're doing things with the conjugate eigenvalue, that shows to me you don't quite understand our thought process yet. because you don't need to use the -2 minus I. You have everything you need with just the -2 plus I, right? We've got our two linearly independent solutions to this second order problem. So I think everybody here can get this, but almost everybody here needs to spend about an hour studying this, right? But you're not alone. There's many, very often people don't get that the first time through. This here, I'm sorry about the typo. Some of you just ignored it and just did what you're supposed to, just like anticipated what I was looking for. I mean, that's good, I guess, and bad at the same time. But that was supposed to be a 1, not a 2, right? And again, it's basically just the matrix, the magic formula applied for either 3 or 7i. And so I get these and this and this, and then the real part and the imaginary part of the a plus ib thing. And I think I forgot to scratch out the, where did my, I did. I guess I whited out the A4. I had like a 4 somewhere in here. I fixed it, I guess, but. Any questions? You can jump in at any point. Okay. I think all of the points people lost here were because they didn't differentiate correctly. So by and large, I think we're good in this problem. And most of you got this one as well, I think there might have been an algebra mistake by somebody here. Oh, Luke did something funny here. Luke put a 1 right here. He copied it down with a 1, so he had a 13 here. I didn't take any points off because he paid a high price for putting that 13 there. So I felt like it was punishment enough. Yeah. With a 13 there, it becomes a sine cosine problem, and you have to do the arithmetic shifting stuff that we did. But mixed results here. Oh, popular mistake. T plus 3, T plus 3, T plus 3. No. Intuitively speaking, think about it. You have a delta function that hits at t equals to 3, right? So before time 3, nothing has happened. After time 3, things kick into motion. So this turns on at time 3, and after time 3, it stays with us. I mean, it's got to be t minus 3 if we're looking at a delta of t minus 3. Just intuition there. So I know you got lost in the substitution of the formulas, and it's not just one of you. A couple of you did this, and it's not the first time I've seen that mistake. I've made it myself previous semesters, but it's t minus 3, and
Can you scroll up real quick?
yeah, sure. Some of you, I don't know, there's like, people got different numbers over here than 7.
I put in 3 instead of 1. I put in the y prime of 0.
Oh, okay, yeah,
Instead
that's,
of, for the second term, I put minus y prime of 0 instead of minus y of 0.
right. I just docked you guys a couple points for that sort of thing. I mean, if you kind of stuck with it after that, it didn't really change the problem a lot. And it's something you can, we can try to fix, but. This one here, I think most of you had this right, which was good. A couple of you still don't have quite how to do that, how to convert it to unit step function. And if you can't do that, that kind of stops you dead in your tracks, right? But anyway, and then another one of you didn't do the division by s, which is also that's kind of like, see, when Luke put a 13 there, I'm like, okay, well, he made the problem about the same difficulty. Like, not putting the s there makes the problem significantly easier, so I have to take off points. And also, it's supposed to be there. So 1 over s times that. The delta function gives you just the raw exponentials, which is nicer, right? And then math. So basically the partial fractions you face is this thing. It gives you a 9th, an 18th, an 18th. A couple of you got that. And you got 2 of them, but they've got the same partial fractions decomposition, which is pretty sweet. I mean, nice. Excuse me, what are they saying? And so you take the inverse transform, and you get this thing. And I think 2 of you got that. And then I felt the need to rewrite this in terms of Cauchys because it's awesome to write it with Cauchys. But no one did this. But anyway, I feel like this is the real answer. But I did not take off points for not doing that, you know? I'm not a jerk. Well, not in this sense, at least. Certainly. How far?
I'll just ask you afterwards. It's just the thing about the partial fractions that I set up.
Oh, so
I had like the exponential.
yeah, we don't put the exponential in the partial fractions because we have a theorem like e to the minus as times f of s inverse transforms to something, right? E to the minus as is not part of the f of s. So we just do partial fractions on rational functions. The exponential functions s don't get pulled into the partial fractioning.
That may be.
Yes. Yeah, like I don't think it's actually true otherwise. Unless you also put exponentials over here. But then they just cancel. So we'd be back to this again. So, yeah. Anyway, so what's the final on?
All the tests.
Differential equations, right? Yeah. So all of the tests.
So.
Yeah. Not so much test 2. I would say focus on test 1 and test 3. Right. So I don't think I'll ask you guys any energy analysis. I don't think I'll ask you variation of parameters with systems on the final. I'll just stick to what we've had on test 1 and test 3. And oh, there is one caveat: series solutions. I should probably test you on series solutions, but not the Frobenius method. Okay. So ordinary points, fair game. Singular points, not so much. On the other hand, I should qualifier. I might ask you a question about domain in terms of singular points. Like we had questions about find the domain of a function. If you find a solution to a differential equation at a point, what's the domain of the solution, power series solution? So we had that theorem that basically we looked for the nearest singularity in the complex plane, and that informed us how big the solution was, the domain. Like I think that question is reasonable for the final. But the actual execution of a Frobenius, like the Frobenius technique, no. That's overboard. Cauchy-Euler? Sure, that's within bounds, right? I think we even had that on test 1 though, right? So I mean, I should clarify, right? Because Cauchy-Euler is the base case of the Frobenius method, right? They're kind of like stupid Frobenius solutions. The Frobenius solutions where all of the higher terms are 0, and just the first 2 terms contribute. That's what the Cauchy-Euler problem is to the Frobenius method. So anyway, I will try to send an email out about when the final is in here. When is it? Do you guys know? You probably know. Wednesday at 10:30. Do you guys have a lot of other finals that day? So you might be able to take it another time. I'll try to, I can let you take it some other time during one of my other finals if it's helpful to you. So I will send an announcement out with when my finals are, like all of them. And so if there's another time I'm offering a final that you'd rather take the DEqs final, you can just come to that time.
I have it down as 1 to 3 on Wednesday.
1 to 3 on Wednesday. Yeah, I haven't looked at it. I have not looked at it yet. It's on my list of things to do. Much like grading your second test, and sending the solution to mission 7 and 8 to your grader. Now, in my defense, he hasn't asked me for them either. But those are not forgotten. They're just not graded yet. And hopefully, I'll have all of these things and more graded sometime soon. Maybe I'll even have test 2 for you tomorrow. I don't know. If I do, I'll let you know. Thanks, guys. It's been fun. I've loved this room, don't you?
Are we allowed to use the sheet
Oh, yes, you can bring the Laplace transform sheet with whatever you want written on the back for the final. That'd be appropriate, I think.
Is there a, like, is it online that we can download like a fresh version of it, or? Because I already have mine filled up with stuff.
I will work on getting a scan of that sheet. Yeah.
Okay.
All right. I will add that to my. Yeah.
I have to print the entire notes on the back.
Very good. Very good. That's- Well, now I'm going home. I usually stick around and have other things to do today, but my son got a cavity, and so my wife is taking him to the dentist. So it's killed the rest of my schedule today.